Uh, so, good morning, Avkash.
Good
Uh,
morning.
Today, first of all, I want to introduce Dr. Avkash. Dr. Avkash is the CEO and founder of SAGE, a sustainable approach for green environment. He is also a visiting faculty of SIH College, New Mumbai, and GN Kansala College in Mumbai, Maharashtra. He received his master's and PhD in environmental science and engineering from IIT Bombay in 2016 and has worked as a teaching assistant for 5 years. He has worked in collaboration with Aarhus University, Denmark during his PhD. His areas of expertise include air quality management, development of an air quality framework, application of air quality modeling at the urban, regional, and local scales, meteorological modeling and forecasting, air quality forecasting, vehicle pollution modeling, evaluation of control and management strategies for air pollution sources such as industrial and vehicular sources, and source apportionment. He has published more than 2 dozen articles in reputed international peer-reviewed journals and many more in national and international conferences. He is also a reviewer for many journals. So this is all about Avkash. Now, today he is going to give a talk on air quality management for Clean Air Action Plan. So, Avkash, it's up to you.
Yeah. Thank you, Sika. Thank you for your introduction about me. And today I am going to talk about air quality management for air action plan as expert talk. So my personal expertise in air quality management using modeling and prediction, and then what kind of action plan we can impose in the system so that we can decrease the air pollution impact. So I'm going to start with few topics that how air pollution is important and why we are concerned about air pollution. So first I will talk about the impact of air pollution, how it is going to damage to our environment, our health, and then I will talk about the how to do air quality management. And there are some criteria for air pollution. There is some kind of system that we developed how air pollution occurs in the system, the sources and all. Then I will talk about some what kind of air action plan can be taken for the urban region. So I'm going to start with this topic, this heading like air pollution and its impact. So this is the WHO report for 2017. So here they are showing number of death by risk factor, and it's Indian study. It's for India. The data is shown for India. Here we can see the air pollution outdoor and indoor. So death due to air pollution outdoor and indoor, we can see 1.24 million. And then if you see outdoor air pollution, it is around zero point 0.8 million. So again, we can see some indoor also indoor air pollution. There are something zero point 0.4 million. So here we can see there are couple of deaths just due to air pollution. Apart from that, there are many disease which is caused by air pollution. So if you see the total air pollution, death by the total air pollution is responsible for 5 million deaths each year. This is approximate we are saying as per WHO report. And globally, outdoor air pollution is responsible for 3.4 million premature death annually in 2017. So we are talking, if you see the data of 2017, it's 3 million premature deaths. Apart from that, air pollution contributes to 9% of the death globally, and this varies from 2% to 15% by country. So if you see, almost 10% death we are getting in the overall the world due to air pollution. So that's why we are concerned about air pollution. So if you see Indian government, they are concentrating a lot on the air pollution. Somehow if you see the other part of the environmental pollution like water pollution, government is able to handle because they have developed such system, and that is easy to control also. So like water pollution, they have controls, they have system they have developed, and that is able to control the water pollution. So now there is big challenge with the world for air pollution. So whole India is working for various technologies, various type of system, assessment, innovation for air pollution sector. Sorry. So air pollution, we are continuing that heading that if you talk about urban air quality, so growth of demography of India is increasing rapidly in urban region of the country. So air pollution in urban area is increasing. So we all population are heading to the urban area, and it is causing the air pollution, because in urban area we have to stay, we have to, whatever we will do, that is cause air pollution. Like we want to travel from one place to another place, we have to take a vehicle will cause air pollution. If you want to cook food, so that will also cause air pollution. So if you want to do anything, there is an indirect or direct source of air pollution. Urban pollution loads are governed by emission density and meteorological condition. Urban area is dense by population, dense by urban infrastructure. So urban area sources are non-point issues. So it is difficult to control and model. But our mathematical equations are developed based on some assumption, some kind of correction, and we develop mathematical model to estimate the our system, how system is working. Once our mathematical model is uh, more or less is predicting our system by mathematical model, mathematical equation, then we'll do some kind of implementation for correction of implementation of the law, implementation of the control system, and then we assess by the model. After that, we go for decision making. 55% of the world population are living in urban area currently. This is a UN report. This has been come from UN report. We can see almost half population are in urban population. Then urban area consume nearly 75% of global primary energy supply. So if we see urban area which having 50% of the total population and 75% energy consumption by globally. So we can see that how urban area is concerned about air pollution. There are some source of air pollution. These are point source, which is emitted by a stack, that is called point source. Then line source, generally it is called by caused by vehicles. In line source, aircraft also comes, but at the same time, the height of the emission in aircraft, it varied a lot. So that is part of line source only. But if you want to do modeling for vehicular sources and aircraft, both are different. Area sources, we suppose there is such area which are being burned or some kind of combustion system is going on. So that is called area source. Flare source, we can see here, flare source, generally it is happened in oil and gas industry. So like BPCL, HPCL, they have such kind of system. Whatever garbage comes, they flare it. Before that, now the government is imposing to control the air pollution from this system. Volume source, generally it is caused by the chemical industries. Like there are n number of sources, n number of leakage, or n number of some kind of hole that cause that is point for the releasing of the gases. And sometimes it happens in at one place there are many release points. So this is called as a volume sources. Generally it is occurring in chemical industry mostly. And then if you want to do modeling or any kind of management plan or action plan, we need to convert all kind of sources in grid wise, so that we can increase the area of interest by globally or country level or region wise. So basically, if you want to do some kind of area study, we should go for the grid wise emission inventory. Now, ambient air criteria, it is given by CPCB, WHO, European country, and then US EPA. So there are six pollutants basically. So if we see 2008 or 2009, before 2008 or 2009, so suspended particulate matter was the air quality criteria, but now it has been removed after 2009. So new air criteria for India is RSPM, that is called PM10, then PM2.5, sulfur dioxide, oxide of nitrogen, carbon monoxide, and ozone. So these are the six air quality criteria is concerned. So there are six criteria, and then the government has set up some ambient air quality standard, NAAQS. So ambient air quality standards are given by Central Pollution Control Board. So they have given for 12 parameter, 12 parameter like SO2, NO2, PM2.5, PM10, and other things. So they have given uh, annual basis and 24 hour. And for few pollutants, they have given for 8 hours and 1 hour. Apart from that, they have segregated with industrial, residential, and rural region, and then ecological sensitive area. So, and they have given, if you want to do measure, if you want to compare the results and standard, then they have mentioned the method also. Like if you see sulfur dioxide, so they have given 50 microgram per meter cube for annually, and for industrial residential area. And if you want to compare for 24 hour, so it should be not more than 80 microgram per meter cube. For same thing for ecological sensitive area, they have given for 20 and 80 for annual and 24 hour respectively. And for that, they have given some method also. Similarly, they have given nitrogen dioxide, particulate matter, PM2.5, PM10, and if you see the ozone, the fifth pollutant, they have given for 8 hour and 1 hour. Why they have given for 8 hour, 1 hour? They have not given for annually, because it is highly reactive. Ozone is highly reactive in atmosphere, so they have given for 8 hour and 1 hour. Then carbon monoxide they have given. So carbon monoxide also it is reactive. It can get converted into CO2. So they have given for 8 hour and 1 hour also. Ammonia also they have given for annual and 24 hours. And now benzene, benzopyrene, arsenic, nickel they have given annually, because 24 hour is very difficult. It's rarely found in the atmosphere. So they have given a standard for this also. Now, characteristics of air pollution. Area, if you see the aerial source of air pollution, it is very difficult to control. And if you see the air, like air is a free resource, no tax. We think that, oh, air is free, who want to pay? So we don't care about air pollution and what quality of air, and we don't think we should not pollute air because it is free. Like if we see the water, so we concern about we should take care of water, because when you want to drink water outside, then we have to pay 20 rupees for 1 liter. So air, very fast rate of transportation. Of course, it is atmospheric process, so it is very fast, can it travel to one place to another place, and large scale of motion. So based on that, it had been classified by in three category, like local, regional, global. So local means it's micro scale, major scale, and macro scale. So local means micro, regional means major, global means macro. So this macro, major, and micro scale has been given in kilometer also. So if less than 10 kilometer, it will be micro. If above 10 kilometer to 100 kilometer, it will be major, and above 100 kilometer, it will be micro. That is global. Air is irreversible process, and it cannot be treated or rejected. Only natural removal is process. So if you want to clean the air, we need to put plant. That is natural process, and only plantation or trees can treat the air. Now I'll talk about how air pollution is concerned, and air pollution affect how it is damaging our health. So one case study done by us in collaboration of IIT, NIRI, and Department of Environmental Science, Aarhus University, Denmark. So this study is about air quality mapping using GIS and economic evaluation of health impact for Mumbai city. So this study was carried out for the year 2012. So air quality monitoring data were used for this study for 12 locations, and we have taken annual average. So there are three body for air quality monitoring in Mumbai: Birhan Mumbai Municipal Corporation, that is MCGM. Uh, MCGM means Municipal Corporation of Greater Mumbai. Then NIRI, CSIR NIRI, and MPCB. So BMC, NIRI, MPCB, all they do for 12 locations only. So few locations are done by BMC, few locations are done by NIRI, and few locations are done by MPCB. So then all data, annual data were taken for the health impact assessment, and then we use this data with population and some factor. Based on that, we can estimate the health impact, and we can assess the cost of this also. Now there is some introduction of same thing. So I'll skip now methodology. So we have to collect the monitoring data, and this should be done by GIS, because here we have done air quality mapping also. So air quality mapping required some GIS study. So GIS format we have to create. So shape file is the format which is used in GIS. So whatever Excel data is there, that we have to convert in shape file. So once shape file is created for the point, like we have created 12 point as a monitoring station, and all 12 point should have attributes. So attribute has been given as a terms of air quality data, and then we have to interpolate. Interpolation generally we did, there are many interpolation techniques in GIS. So all has been used, and we have compared the results with observed data. Like 10 we have interpolated, and rest 2 were kept for the comparing. And then we have seen which interpolation technique is better. After that, we have done health impact assessment, delta JP. Delta HJP means health impact. J is for the health impact assessment, and J is for the pollutant. For pollutant, sorry, health impact J means J is the some particular disease, and P for the pollutant. And BJP is the concentration response coefficient, and population POP is the population for the particular location, and delta AQP is the air quality change for the particular pollutant. So P is the pollutant, and J is the particular disease due to air pollution. And this CR coefficient has been taken for Mumbai city as a local data. So this could be this should be proper. So this is the some methodology we are showing in the map. So base map was prepared for the Mumbai region, and then georeferencing was carried out. Once georeferencing has been done for base map, then we have to create shape file. After shape file, we have to put Mumbai outline and monitoring station as a point in shape file. Then digitizing the map, then attribute entry, interpolation technique, then results. So this is our map after the GI shape file, and shape file after the interpolation we can see in this format. Now result and discussion, we can see the results in tabular form. The winter season wise air pollution concentration, like SO2 we can see this 15.7 microgram per meter cube. The unit of these numbers are microgram per meter cube. This is a standard way we have to we present in microgram per meter cube. So an annual is also given. We can see the winter season are maximum in the concentration term for air pollution. And same thing has been presented in the map also. So if you see the visualization wise, this map has been presented for the annual way. So this for this annual way for each location we have presented. And this table is for whole Mumbai. So now once we have done the interpolation technique, there are few interpolation techniques like IDW, inverse distance weighting, then Kriging spherical, Kriging Gaussian, spline. These are the 4 interpolation techniques inbuilt in the GIS. And the another thing we observe. So what we are doing, we are interpolating few data, and then we are comparing with the 2 locations, that is called Bandra and Sion. So in these 2 locations we are not included for the interpolation, and we are just validating this data. So for SO2, NO2 and SPM, we can see the IDW kriging are more close to the our observed data. This is the overall conclusion of this study. So IDW is this and observed is this. Here we can see the green is kriging Gaussian is close to the our observed. But here at Bandra location this is our observed and close we can see the spline. But spline is close will be this red one. Red one is kriging spherical. So if you see the SPM, the kriging is close to the observed. But if you see the NO2, the observed is this and our spline is here. So you can see spline is the close to the observed. But here we can see most of the cases this is our observed and this is our IDW. So mostly IDW and kriging are matching to the observed data. So here population of the Mumbai city, because now we are going to assess the health impact, we should have population data. So population data has been presented in the map here. Now baseline is the concern to the what baseline we are taking for health impact assessment. So baseline will be taken as there is no impact at this air quality level. So this we have taken very neat and clean from the base map, and that has been taken from the another model, that is Danish Eilerian hemisphere model. So for northern hemisphere model was carried out, and we found that this much concentration for SO2 or NO2 2 microgram per meter cube from the regional sources, and this has been kept as a baseline, and 17 microgram from the for the PM10, but we have taken 57 this 40 microgram per meter cube as 57% particulate matter are from marine sources, because Mumbai has some marine contribution also. So this is the baseline concern, and we can see this the difference between the concentration that for particular location annually. Now this is the exposed population. So here we can see where is the exposure of health in Mumbai city. So for various locations we can see here Devnar and Andheri for SO2 it is maximum. And if you see the PM10 Maravali, like near Devnar only, so it has maximum maximum health impact. And Andheri also we can see, Devnar also location where population health impact is more. Andheri, if you see the NO2 is maximum, because Andheri is dense vehicular population. So because of that, it is more health impact assessment in Andheri. Now cost wise, in cost also, we can see here this NO2 and PM10, because cost data was available for NO2 and PM10 only. So here we can see the cost of the particular health, COPD, and this for all the cost for particular health disease has been given here. So Andheri is maximum for NO2, Maravali is maximum for PM10. Then same thing has been presented in the map. So here we can see this map is Maravali, Devnar and Andheri are maximum in the terms of cost. This is the conclusion that I said. And here it is the total health cost was estimated as 8,000 million, that is called 8 billion USD, to and PM10 pollution in Mumbai city for the 2012, and that is the 4.2% of the Maharashtra state GDP. So another case study I am going to show. I will go in fast. For this is similar study for ammonia only. So there are ammonia is the concern about there are a location in Mumbai that is called Devnar Maravali. So there is a dumping site that is a major source of ammonia, and there is RCF industry also. So because of that we got interested in this NS3 study, ammonia study. So we can see this maximum concentration during July, because this time maybe this demand for the RCF industry, the chemical fertilizer industry are more, so they are producing more ammonia release in atmosphere. This is the seasonal concentration and annual concentration are given. Same thing has been given. What we did, we removed including Marawali. This map is including Marawali, and then we can see the picture of the Mumbai city. And average is coming 8.5 microgram per meter cube. And when we are excluding Marawali, getting and our average is coming 56. So of Mumbai city. So if we see this, it is very different numbers, and here we can see the maximum concentration of Marawali is 342 microgram per meter cube annually, and that is the 6.1 times than average of whole Mumbai city. And if you compare this average concentration, including Marawali, excluding Marawali, this is 1.5 times. So that's why we were concerned about ammonia for Mumbai city. Now again, we have done for exposed population by ammonia health impact assessment basically. So here you can see, of course, Marawali, Deonar will have maximum exposure due to phlegm and other chest illness by ammonia only. And then health cost in USD that we can see here. This is the maximum in USD million. Almost $25 million are the cost of this Philcom only. There are some conclusions that I already explained. Now I will talk about this evaluation of control strategy of industrial air pollution. So if there are air pollution, how we can control? So if we see the industrial area, we have only industrial sources. It means so industry they use some kind of fuel to burn it, and then they discharge it to some atmosphere through chimney. So our zero to end process, we can see there is something to fill it as a fuel, and there is discharge into the atmosphere by chimney. So there are 2 points. So this study already had been published in the journal. Actually this is some study introduction that we use air quality modeling for this study, and that US EPA model air mode has been used for this study. And when we want to do air quality modeling, we should have meteorological data that has been taken from WRF model, weather research forecasting model. It is one of the complex model, and it requires high performance computing. So the beauty of a WRF model is we can generate on-site meteorological data for the anywhere, any global, at global level. We can reduce the resolution of horizontal sites. Like if you want to get meteorological data at 3 by 3 kilometer size, so we can downscale it. So Chembur was taken because Chembur is the area where industry are more, and there are 4 big industries, that is called HPCL, BPCL, RCF, and Tata Power. So these are the major industry in Mumbai, and all are situated in the Mumbai city, Chembur only. And also, as per the CPCB report, the CEPI, the Comprehensive Environmental Pollution Index, is 69.19. That is as per CEPI 2010. So that's why we taken this study area. Several control strategies have been proposed for industrial sources, like cleaner fuel substitution, change in basic production process, and shifting our industry outside of the city. Since industries of Chembur region are already existing and industrial and commercial zones are preset in the domain, so in the present study, not all control strategy can be applied. So here so we can't include all the control strategy. So this is some detail about the Chembur region. Here is our RCF, Rashtriya Chemical Fertilizer Limited. Then here is the BPCL, and this side is the HPCL, and there is Tata Power in this region. So whole industry are in this region only. There are 6 major road, VN Pura Road. This is some BD Patil Marg. This is the NG Acharya Road. near railway station. The Ghatkopar Manapur road, this big road. This the methodology of this study, like industrial air pollution source taken, then WRF model has been used for the generating meteorological data on site that has been fed into AirMet. AirMet is the pre-procedure of air mode, and there are another pre-procedure of air mode is AirMap. So that deal with the digital elevation model terrain data. So that has been taken from SRTM DEM file, and then when once we operated the air mode, we got air quality data for existing scenario, we validated it, and after the validation we applied some control strategy like change in stack height and change in fuel. There are two strategies we have used in this study. Only two control strategy are applicable for this study because all the regional area are set. So then change in air quality control scenario from existing scenario, then selection of control scenario, which scenario will be better in the terms of impact. So this is the WRF model. I will not go in detail. So generally there is a data, input data that has been taken from NCEP FNL Operation Global Data. So and the resolution was 25 kilometer for this study. There are some schematic parameter so that we have taken this. Now, once we have done air quality modeling, so we got this for data for SO2, NO2, and PM. This is our SPM. You can see that we have taken only industrial sources. So maximum pollution we have got at this center point only. This is for annual. So here air quality modeling for control scenario, we have two types of scenario. One is the once we increase the 10% stack height, that is scenario H1. Scenario H2 is increasing the 25% increment of stack height. Scenario H3 is 50% increment of stack height. Scenario F1 is low sulfur. We have to change everything to gas. Means if there is LSSS, we convert it to the gas. If there is coal, convert to the gas, and gas to no changes. And F2 is if there is LHSS, convert it to LDO, that is less emission fuel. Then if there is coal, then convert 50% on coal and 50% on gas. And there is gas, there is no changes. So this 5 scenario we are considering. We can increase more than 50% of stack height also, but we can't do as the economically it may not be feasible. We will show in the study. So this study we show this here. Okay. So control management strategy have been applied for industrial sources and modeling has been done for reduction of air pollution level. The modeling has been done for hourly, annual average, highest daily average, and highest hourly average. The above 5 scenarios have been applied for NOx and PM. Only scenario H1, H2, H3 have been applied for SO2 and a scenario F1, F2 cannot be applied for pollutant SO2 because SO2 emission data were not available for fuel changes in literature for Mumbai city. Suppose as for SO2, what will the changes the fuel for emission terms? So that was not given. So we have not used. So this is the predicted hourly annual concentration for control scenario. So maximum concentration and change in concentration for various control scenario. So if you see the current is 8.57. If you are changing the this is the maximum concentration only, a percentage change in concentration. So we can see here maximum reduction we are getting in H3, that is the 50% stack height. Similarly, we are getting for PM also or SO2. We did not apply F1, F2 as it said data were not available. So here we can see 42. That is the maximum one. Of course, we will increase the height. We'll get the reduction of concentration data at ground level. And this is the reason we did not exceeded the 50% of the stack height, more than 50% of the stack height, because if we are increasing the after 50%, concentration reduction is very less. So we have stopped to the 50% only for each pollutant. Now same thing has been done for predicted daily 24-hour maximum average concentration. Here also we can find the H3 having maximum concentration reduction in all the cases. And then if you're taking for maximum hourly concentration, so here also we can see maximum reduction at H3, that is 50% increase in stack height. So overall, what we are saying, the after increment of 50% stack height, the reduction of rate of pollution level are low, so it is not cost effective. So to have further increment of stack height, it will not be cost effective. Sorry. So as per the last slide, this slide, we can say that if we increase the more than 50%, our cost will increase, but reduction in air pollution will not be more. So we are not moving forward with increase of stack height more than 50%. So similarly, scenario F1 seems to be best for all pollutant, for all cases, for fuel changes only. So overall, S3 is not based on the source emission reduction strategy. However, scenario F1 is based on source emission reduction. So here S3, if you are increasing the height, the emission will remain same, since it will get the dilution time as we are increasing the height of a stack. So ground level concentration is low. So we are recommending the scenario F1 is the best on the emission reduction. So overall, we can say that F1 seems to be best option for all pollutant, as F1 is the emission reduction strategy. Now, what we can say, uh, this Indian, along with IIT Bombay, to control the air pollution, we developed some kind of air cleaning system that is called ASC, Ambient Air Cleaning System. So here our team and IIT, including the professor, developed these devices. And the feature of these devices is uh, air will be taken from outside from the system, and then it will pass through the, there is inlet and there is some kind of filter, and it will suck from the here, and then there is a coated carbon that will reduce the gaseous pollutant, and outlet will be above this. So in from top, clean air will be discharged. So there are three model in this such kind of system. Like this is the only for the particular matter, and this is for the air clean tower we are saying. So this can intake high volume of the air and clean at certain time. And this was inaugurated by our union minister of the country. So this was the presentation. Shikha? data was used here also. So here what we did, this is our Chembur region in Mumbai city. So this zoom has been done here, and this is the terrain data for this region. So here we can see this is the maximum terrain, and this is the not maximum, where industry is more. Then again some detail of the Chembur region. Then schematic data flow, WRF model, what we did meteorological modeling, and then meteorological modeling through WRF model. So we got one data was from the meteorological from modeling, and one data from the meteorological observation. So that both data were compared, and then we put both data in the modeling in AirMate through air mode, and then emission inventory and digital elevation file was used in our air quality modeling. Then predicted the concentration for NOx and PM. We compared the results, and then we evaluated the model. Then again some data collection source, how we got the data. Then emission inventory, like when we prepare emission inventory, so for road we need to have data for the number of counting and all. So this is the way we presented the emission inventory. For BN Pura road, we have various type of vehicles, and that is shown here. And then after all this, there are emission factor, emission inventory prepared through the number of vehicles, emission factor of the vehicles, and there are length and all. So based on length, we have we got this emission inventory in gram per second. So this is the for NOx and SPM. Generally, it is PM only, and mostly PM10 comes from the vehicles. Now total emission for the detailing emission vehicle, detailing emission inventory was shown here. Same thing for the various sources, various type of vehicles, because here we are going to estimate the rank of sources. So this is the total emission for the Mumbai city. Like SO2 emission, we can see from industry it is contributing 97.5%, and domestic is contributing 2%, and vehicle, cremation and everything they are contributing 0.5%. In NOx emission, we can see 64% contributed by the industry, vehicular is contributing 17%, and domestic sector is contributing 18%, and cremation, bakery, hotel is contributing 1%. If SPM emission load, we can see 3% from the vehicles, and vehicle means tailpipe emission, and cremation, bakery, hotel are contributing 3%, and remaining are contributing by industry only, that is 94%. Now result and discussion. This is the comparison of the meteorological data that one we got from the WRF model, and one we got from the observation. So we can see almost they are same. There are some data error also, that also has been shown here. Now this is the windrows that has been taken simulated by WRF model, and this is the data from IMD. So this data we can see there is some difference. This is because we have taken 25-kilometer domain, and this wind direction may be almost similar, but wind speed has some gap. And when we take IMD data, it has low wind speed, because there is terrain. Because of terrain, we get low wind speed. There is always gap in prediction and the observation. Now this is for the this windrows was for the annual windrows, and now this is for only for May months. So here we can see direction is almost 45 degree away. Of course, wind speed also there is gap that we say. So here what we are saying, the concentration of SO2. So this is the for current year, what is the concentration for SO2 for the particular region. So that we got it here. And there is some concentration, simulated concentration, observed concentration. Then same thing has been done for NOx also. There is a simulated concentration, observed concentration. Then SPM also we got this the simulated concentration, observed concentration. So then what we are showing, how much industry is contributing. Like simulated concentration we got from at BPCL and HPCL location, and then ambient observed concentration. So if you are taking only industry, then this is the concentration. If you are taking ambient observed concentration, that is 26. So it is coming 18% from the industry and 36% from the industry only, but at HPCL. So we can do this comparison, this contribution analysis at certain point. We can't contribute at whole area. Same thing has been done for SPM also. So at BPCL, HPCL, we can see this 67% and 42% contribution respectively from the industry only. Now we are going to assess from the for the vehicular point of view. So how much vehicle is contributing for the this region? So here we can see we had one comparison thing like concentration of ambient air quality from all sources is 53, and concentration of contribution in ambient air quality from vehicle is 13%, and this is coming around 25%. And that was for NO2. In SPM, you can see 45% contribution for the region. Then we are going to say like NOx contribution from the diesel vehicle, how much they are contributing for 28th May, for particular day we are doing. So here we can see 34% contribution from the diesel vehicle mostly. And for SPM, this is for SPM, it is contributing 96%. So this is the summary and conclusions. The aim of this study was to generate meteorological profile to use them in air quality modeling for air pollution mapping of Chembur area. So generally WRF model is applied for weekly simulation, but in this study it has been successfully used for annual simulation. It can be generated on-site data for the any meteorological profiles, and we can save the resources also. Like if you want to buy the data, it has a huge cost. If you want to install the meteorological station, it has a huge cost. So using this model, we can save some resources and time. An emission inventory was assembled for this study area. The integrated model was applied for simulation of annual average for all sources, one month for industry and 1 day for vehicle. So what in this like say that from vehicle sources we did for 1 day modeling, for industrial sources we did for 1 month, and for all the sources we did for whole year. So this was some kind of decreasing the time scale for the vehicle kind of all type of sources or air pollution sources. Results were used to figure out the area with critical concentration and relative contribution of various sources to ambient air quality. The air quality concentration results can be used for prioritizing the control strategy in the study domain. Now here we are comparing the emission load versus the concentration load. Here we can see that I discussed also in previous slide. In NOx emission, cremation, bakery, hotel, and restaurant are contributing 1%, while domestic contributing 17%. Diesel car and diesel vehicle, they are contributing 5%, and other vehicles are contributing 13%. Industry are contributing 64%. If you see the concentration point of view, domestic and other are contributing 47%, diesel is contributing 9%, other vehicle is contributing 16%, industry is contributing 18%, as they have their stack and they have some kind of dilution factor, so they are getting impacting less in ambient. In SPM emission load, if you see, 94% from the industry and 3% from the vehicle and 3% in the other emission sources. While if you see the concentration, they are decreasing in the concentration in 50 to 50% from 94%, and vehicle is contributing from 3% to 5%. If emission load, if you see 3%, but ambient concentration is 5%. And other vehicles you can see other vehicles it's 45%. That is here something. The whole vehicle is 33% is showing. Here you can see LDDB and other vehicles showing the maximum thing as 45%. So this was the another case study. So I'll close here. I think my time is also up.
Yes, Avkash. Hello.
Yeah, yeah, yeah.
So it's
Hello.
over. Okay.
Yeah,
Is it over, Avkash?
yeah. It is over. It is over.
Okay, okay. Thank you. Okay, okay. Thank you, Avkash. Thank you for the nice presentation. Your slides were very insightful, and you have given us the scope and how can we manage the air quality here, and how can we guide the students here for air pollution research. So these slides are very insightful. So thank you for sparing time to for expert talk.
Yeah.
Hello.
Yes, yes.
Okay.
Thank you, Shikha.
So thank you.
Okay,
So you can leave the meet.
okay. Thank you.
Okay, sure.